So this is 6.2 of physics, optics. This focuses primarily on diffraction, which is the spreading out, which is basically something spreading out from a small opening. This can be anything, but this section of the chapter will primarily focus on light. And to review light, from 6.1, light has a wavelength, frequency, period, and speed, which all play a role into the diffraction of light. When light diffracts, it can be destructive, or it can have destructive or constructive interference. For constructive, this is shown when the waves of light are on top of each other, and destructive interference is shown when the waves are spaced out a pi's length away from each other or 180 degrees. This is a cancellation of the light, which the most extreme terms, if the peak and the valley of the curves add, it will add to zero, meaning there will be absolute diffraction or zero light. An example of this in real life is with noise cancellation headphones. If you are on an airplane, you hear the roar of an engine from a plane, and you turn on your noise cancelling headphones, what will happen is the noise cancelling headphones will pick up the sound wave from the engine, and it will try to basically mimic the sound and space it out 180 degrees or a pi's length away from that to match the frequency of the sound, in effect to cancel it out. So the first type of diffraction I'll talk about today is double slit diffraction. This is when light projects or goes through two slits. So what happens is after you shine a light through these slits, through like a laser or something like that, two new light waves will be projected from the initial one, and what will happen will now these two light waves will interfere constructively and deconstructively, and that's shown by the curve drawn opposite of the slits. As you can see, the middle, it's the most bright, and as you continue in other directions, it dimmers out. So the topic of destructive and constructive waves is directly connected to the delta R value of one of the light waves. So bear with me because this is a little bit complicated. This is the difference in path length that one wave takes to get to the wall. Essentially, other than in the exact center of the wall, one of the waves will have a longer distance to travel than the other. When the delta R is 0 or an integer, it will interfere constructively, and that's shown by the larger curves opposite of the slits. And when the delta R is some form of 1/2, 3/2, 5/2, etc., it will interfere destructively. The equation we use for this is delta R equals d sine theta, which is equal to m lambda. All these are equal to each other, and what each variable means I'll put it on the screen. There's not really a good example, real-world example of where double slit diffraction is important, but there are for diffraction gradients, which I will talk about next. So for the next diffraction, let's discuss diffraction gradients, or gradients, or gradients. Gradients is what it's called. Anyways, so basically, diffraction gradients is when there's a lot of different slits, not more than two, more than one, just basically like 100, 1,000. There's a lot of slits as to where the light goes through. And basically the most interesting part about this diffraction is that on the opposite side of the wall, the waves either interfere perfectly constructively or perfectly destructively. So basically, any points, this is kind of similar to the example before, any points that are not an integer of 1, 2, 3 of their wavelength away from each other will be total darkness. So like the halves, the 3/2, the 5/2, that will be totally darkness, whereas 0, 1, 2, 3, 4, 5, etc. will be bright. Also, something to note is that the brightness is not strong in the middle. That's a difference from the single slit diffraction. It's actually uniform throughout on the wall opposite of the slits. Also, the number of slits n, that's the variable we use for the slits, is proportional to basically how skinny and bright the light is. So if you have less slits, it's less skinny and less bright, more oblong, and if you have more slits, it's brighter and skinnier. The equation we use for this is actually the same equation that we used for the previous one. It's d sine theta is equal to m lambda. This gives the constructive points for a diffraction grading interference on a wall. For a real-world example, of where you can find diffraction gradients. It's a little bit weird to find, but if you look at a CD or DVD, the closely spaced tracks on a CD or DVD act as a diffraction gradient to form the familiar rainbow pattern. So something I didn't mention purposely was how basically why there's only small or how there's only blimps of light because of how the light interferes destructively. I've linked and time-stamped a Khan Academy video that explains this very well. I recommend you watch this to understand that. So lastly, I'll give a quick summary of single slit diffraction. This is when there's only one slit in comparison to the previous examples where there is two or more. So yeah. So important to note about this is that directly opposite of the slit is where the light will be the most intense or the most bright. It's also important that the slit is not larger than the wavelength of light itself, or else it won't work correctly, I guess. Also something to note is that when m equals 0, or aka right across from the slit, it's not destructive, meaning n is also the most bright, like I said before. However, any other integer, such as m equals 1, m equals 2, 3, these are destructive, or you could say these are where there's no intensity or no light, shown by the lack of a wave. For this type of diffraction, we use the equation W sine theta is equal to wavelength, or lambda. W stands for the width of the entire width of the slit. Currently, we do not have a formula for where there is constructive interference. However, we can find the width of the bright spots, but not their location. To end this YouTube video, I just want to give a shout out. Not that anyone's gonna recognize the shout out, but I want to give a shout out anyways to Khan Academy. I use them to understand the content. I recommend you do the same if you were to watch this video. Specifically, I would watch and try to understand why waves cancel each other out with destructive interference. I think that's the most interesting part on how to wrap your head around, and that's what makes all of these different slits different. Thanks for watching, and I'll catch you in the next video. Bye.